Carboxylic acids are pretty unreactive for the most part, and one of the ways they can be made more reactive and therefore be more useful in organic syntheses is by converting the acid group into an acid chloride. The textbook method for this conversion is to react it with thionyl chloride, producing sulfur dioxide as a byproduct. However, thionyl chloride is a fuming toxic liquid about as hazardous as bromine that's hard to come by for amateurs and even harder to homebrew. Preparing it involves reacting sulfur chlorides, which allegedly smell like death, with sulfur trioxide, which is basically concentrated sulfuric acid's bad uncle on steroids. Neither of these are materials I ever want to deal with if I can possibly avoid them. Another method involves using oxalyl chloride, which is similarly hard to find in homebrew. Homebrewing it requires phosphorus pentachloride, which is pretty nasty in its own right and is also a chemical weapons precursor. And preparing phosphorus pentachloride requires chlorine gas and red phosphorus, the latter of which is highly restricted due to its use in meth manufacturing. A much more accessible and less hazardous method was published in 1979 by Venkataraman and Wagle. This involves dissolving the acid along with cyanuric chloride in acetone, then reacting it with triethylamine, removing the solvent and redissolving the acid chloride with a non-polar solvent, this being the only thing left in the mixture that's soluble in solvents. Cyanuric chloride is relatively accessible and quite cheap, making it an attractive alternative to either thionyl chloride or oxalyl chloride. The reaction is based on earlier findings that cyanuric chloride was observed to form acid chlorides when reacted with acids over long periods at high temperatures. The authors modified this procedure by using triethylamine to liberate the acid chloride from the intermediate complex, allowing the reaction to be run at ambient temperature. As a bonus, if the desired end product is an ester or amide, the necessary alcohol or amine can be added directly to the reaction mixture and the final product can easily be isolated from it. In this video I used this method to convert benzoic acid to benzoyl chloride at a scale of 1/10 of a mole. The reagents used were 200 grams of acetone, 20 grams of anhydrous sodium acetate, 12.2 grams of benzoic acid, 9.2 grams of cyanuric chloride, 10.5 grams of triethylamine, 50 ml of hexane, and a special guest, 20 ml of dichloromethane. As water is the slow and subtle nemesis of acid chlorides, the first step was to dry the acetone by distillation over sodium acetate. The Science Madness wiki, which was where I got this recommendation from, also recommends a second distillation over anhydrous magnesium sulfate, but in practice I found that's not necessary. Once the acetone had been dried, benzoic acid and cyanuric chloride were dissolved in it. Both dissolved within a matter of seconds. As an aside, the cyanuric chloride powder generated a lot of very fine and extremely unpleasant dust when handled. After the first attempt, I made sure to use a dust mask. An addition funnel was fitted to the top of the flask, and a thermometer was fitted into the side arm. The addition funnel was loaded with triethylamine, which was added dropwise. As soon as triethylamine addition began, white precipitate was formed, and it soon filled the flask. A key detail the paper doesn't mention is that the reaction is quite exothermic, which is why I added the thermometer. The mixture started at around 20 degrees, peaked at about 30, and after the addition was complete it was left to stir for 3 hours. It was then filtered by vacuum in short bursts. Continuous running would have resulted in a lot of solvent boiling off. The filtrate was then concentrated by distillation of the solvent. As the solution got more concentrated, solids precipitated out of it and it turned opaque. Distillations were stopped when the temperature at the stillhead started falling. Once the mixture was cooled to room temperature, hexane was added to the viscous sticky orange residue, and the mixture was shaken thoroughly to extract as much soluble material as possible. The original paper used carbon tetrachloride, but that's very hard to come by these days, and hexane is similarly non-polar. The supernatant fluid was decanted into a smaller flask, though going by the smell, a lot of benzoyl chloride had been left over. On a whim, and because I'd got a very poor yield the last time I used hexane alone, I decided to add 20 ml of dichloromethane to dissolve any remaining product and shift the solid residue. This worked. After filtering the hexane and DCM extracts, then filtering them again because a precipitate formed when they mixed, the solvents were then removed by distillation over gentle heat. Once distillation was complete and the mixture was cooled to room temperature, the last traces of solvent were removed under vacuum. The final product was recovered as a clear yellow liquid substantially denser than water with a high refractive index and a characteristic smell much like that of marzipan, with subtle top notes of chemical warfare. The yield was 5.25 grams, which is 37% with respect to benzoic acid. Compared to the 80% reported in the original paper, this is frankly terrible. The only real difference between this procedure and the reported one was that the acetone was removed from the reaction mixture under reduced pressure in the original paper. I couldn't do this as my vacuum pump has no way to regulate the operating pressure, and the vacuum it pulls is too tight to boil off acetone in a controlled manner, unless you use a dry ice bath. And maybe carbon tetrachloride really is more efficient at extracting the final product than the combination of solvents I used. This aside, the reaction is simple and practical and tremendously useful for amateurs, provided you can get hold of cyanuric chloride. It does, however, have a few key limitations. I mentioned earlier that the reaction is quite exothermic. With shorter chain, more volatile acids, it is very exothermic. When I tried the reaction on this scale with acetic acid, an ice bath was needed during the triethylamine addition to keep the temperature under control, and an awful lot of smoke was formed in the headspace of the flask, likely the salt of the acid and triethylamine. It also took several hours for any precipitate to form, meaning the reaction mixture needed to stand overnight, and it was just a general pain in the arse all round. The best solution here is to mix the precursor acid with benzoyl chloride, form the more volatile acid chloride by metathesis, and distill it out of the mixture. Yields reported in the paper are generally good for monocarboxylic acids, but worse for dicarboxylic acids and acids containing alcohols, amines or phenols, in other words, groups that can react with the acid chloride. The authors reported that the reaction failed completely with malonic acid producing no product at all. My best guess is that the carbon between the two acid groups is acidic enough to be deprotonated by triethylamine, causing the molecule to become unreactive. Based on this result, it seems that it's likely to fail with beta-carbonyl acids in general. Overall, this is a very practical and amateur-friendly alternative to the textbook method, even if the yield I got was poor. I find it strange that it's not more widely known, but then again, acid chloride formation is far from the only reaction where the textbook method is impractical or unnecessarily hazardous. So it goes. I hope you enjoyed this video. Thank you for watching.